Let's take a look at section 4.3, and this one is all about the derivatives of inverse trigonometric functions. With a quick review here, and I think this one is worth going over. It says give the domain and range of the function and evaluate the function at x equals 1. So let's talk about domain and range. And I have given us a picture. First one, it says the inverse sine, what is its domain and range? And when I look at sine, I know that in the original function sine of x, that its domain is all reals, and its range is -1 to +1. So now if I talk about its inverse, I know that its domain is what was the range, and what was the domain for my original function is now the range. They just change, they just reverse. And if I want, where x equals 1, so I want to solve y equals sine inverse of 1. Evaluate the function at x equals 1. And sine inverse of 1 really in my head means the sine of something equals 1. And that would occur at pi over 2. So my y value would be pi over 2. Cosine, like sine, has domain that is all reals. So its domain is all reals. And its range goes from 1 to -1. Say that otherwise, -1 to 1. Let's start small and go big. Now, if I want to find the inverse, I just reverse those, and I'm going to have a domain from -1 to 1. These are expected values that can be put in for the domain, and that allows the range to come out as all reals. Tangent, a little bit different. So tangent, remember there were vertical asymptotes when we were dealing with a tangent value. And those vertical asymptotes occur on the pi over 2 values. So commonly we talk about -pi over 2 and pi over 2. So the domain was excluding the pi over 2 and -pi over 2. And we want to get this down so that it is a function and passes the vertical line test as well as the horizontal line test. So I am going to restrict myself to just this one cycle of the tangent graph so that it passes a vertical line test as well as a horizontal line test. It needs to be 1 to 1. For every input, there's an output. For every output, there's exactly one input. And that will happen if I restrict this. So my domain on sine would be restricted to -pi over 2 to pi over 2. I need parentheses, don't I? Not including endpoints. And the range looks like, well, it goes from -infinity up to infinity. -infinity to +infinity, or essentially all reals. So now I twist this around, and my domain is all reals. And the range is -pi over 2 to pi over 2. Let's always take a little bit of thought process there. And then number 9 says find the inverse of the function. To do that, I'm going to switch my x and my y's and then solve for y. So I think I might be tempted to multiply by y, and that would give me x, y. You know what? I think that's going to create a bigger mess. You know what I'm going to do? Let's separate the denominator, because then I see this is clearing and I get x equals 3 minus 2 over y. And let's keep solving. So I want to, let's separate. I'm going to add 2 over y to the left and subtract the x to the right. And then I'm going to multiply by a y. And then I'm going to divide by 3 minus x. And there is the inverse function. Just switch your x, y's and solve for y. Whoops, too fast. Derivatives of inverse functions. If f is differentiable at every point of the interval I and dy dx is never 0 on that interval, then it has an inverse. And f inverse is differentiable at every point on the interval where I'm looking at f evaluated on that interval. So as long as the derivative was not 0, it should have an inverse derivative. Now, just a review of what those derivatives were. So the derivative of sine inverse was u prime over square root 1 minus u squared. Tan inverse of u, where u is some function probably of x, we get u prime over 1 plus u squared. And the other one, secant inverse of u. Let's take its derivative. It turns out to be a u prime. Basically, the u prime on top is the chain rule, isn't it? Because we're saying let this be some function where u could be 3x minus 7. And this u prime is taking care of the chain rule then on that. Okay, absolute value of u square root u squared minus 1. The other three are going to be cosine inverse of u. Its derivative is identical to sine except that it is negative. So negative u prime over square root 1 minus u squared. Cotan inverse of u, its derivative is negative u prime over 1 plus u squared. And cosecant inverse of u, its derivative is u prime, negative u prime over absolute value u, square root u squared minus 1. Those 6 are good to have memorized. I will say this. I would say primarily those are the 2 that the AP focuses on. Very seldom do you ever find the others, but we should know them. So then example, I feel like there should be a proof. Where is that at? You guys have it in your notes, maybe? Because it is kind of nice to see where these come from. Sine inverse of x. And we want to prove its derivative. So I want to prove that the derivative is u prime over square root. Actually, if I'm just doing x, it's going to be the derivative of x, which is 1. And then I'm going to have 1 minus x squared. So I want to show you how that comes about. So let's start with the equation. Where should we start? Y equals sine inverse of x. Let's start with that and then take its derivative. But before I get things rolling, because if I knew its derivative, I could just take it. So I can't really just say, take its derivative. Let's get rid of the sine inverse. And to do that, I'm going to apply the sine to each side. So I'd have sine of y equals sine of sine inverse of x. And we know then this side, of course, on the left is sine of y. The sine of sine inverse, they are inverse operations. They undo each other, so I get x there. Now, I feel comfortable saying, let's take the derivative of each side. So d dx, we'll take it with respect to x. I want to take the derivative of the left side and the derivative of the right side. We don't do proofs very often, but it really is a good brain activity to do proofs. And I believe in college you will have to do probably more proofs in your calculus career. So derivative of sine becomes cosine of y, but we're with respect to x, so we've got to do an implicit dy dx. Over on the right, the variable is x. It's with respect to x, so that makes it easy. It's just simply 1 on the right. Now, we're going to write dy dx is equal to 1 over the cosine of y. Oh, interesting. So that's, I would like it in terms of x. And how am I going to get that? Well, it would be lovely if we could replace cosine of y, right? What is the cosine of y? I wish I knew. Well, we do kind of know. I'm going to go back to a spot here. From that, I can draw a little picture. I know that the sine of y is equal to x over 1. And sine is defined as opposite over hypotenuse. So if I drew a right triangle, because trig is all about right triangles, and I identified two angles, x and y, maybe not necessarily even x there. Let's just call it y, because y is our angle. Then I have opposite is x, hypotenuse is 1. Can I figure out the adjacent side here? Right triangle, we can use a little Pythagorean theorem. This is one of those techniques I think you did develop in pre-calc. You probably use these triangles to do that. So I know that x squared plus my question mark squared equals 1. The question mark squared would be 1, don't you love that variable? 1 minus x squared. And therefore the question mark is going to be the square root, and I'm going to keep the positive case since it is a length of a segment. I get the question mark then is 1 minus x squared. So therefore, replacing cosine of y from the picture, what is the cosine of y? Well, cosine, I'm trying to think of how I want to write this. Cosine is 1 over adjacent over hypotenuse. And that's going to be, according to our picture, adjacent is 1 over square root 1 minus x squared divided by the hypotenuse, which then simplifies. Finally, we get the derivative of sine inverse is 1 over square root 1 minus x squared. Woohoo! That's what we were trying to prove, right? This has always been given to us. And we were able to do all of the proof to come out with that answer. So things are not just made up, they are all derived, and we very seldom take the time to do that. So that was kind of fun. At least I thought it was fun. The derivative of a sine inverse. Remember last year in AB, we identified our u, and then maybe we did a little bit of work over here. We said the derivative of u is 16x. It would have been a du dx, but we just wrote du. We also found u squared because we need that, and u squared would be, what, 64 x to the 4th? If you don't want to, you do not have to do this setup. I just found it easy in AB to start people out with that. But you guys probably can do the pattern work in your head. There's the formula for sine inverse. So I need u prime. The derivative of 8x squared is 16x. Over the square root of 1 minus u squared, and I can just look back there, or I could look here if I did my little breakout session there, and I get 1 minus 64x to the 4th. I don't think trig, inverse trig derivatives are all that difficult. Here's our u, isn't it? And now I need to know the pattern for the derivative of secant inverse. So I'm just going to say y prime equals It is a u prime over absolute value u square root u squared minus 1. All right, fill in the pattern. U squared is going to be a 3. The u is 3x minus 4, needs an absolute value because this does have the potential of being negative. And then I need to take u, 3x minus 4, square it, subtract 1. And obviously we could simplify that. I don't think it's going to make much difference, so we're going to leave that square root the way it is. Save us a little time today. Cotangent. What is the pattern for cotangent? Cotangent. Y prime equals u prime over, ooh, it's negative, and it's 1 plus u squared. Okay? Challenge yourself. Make sure you memorize those. Now, I'm going to say y prime equals, I was just looking at the way they notated. That's kind of weird notation, but we'll go with it. This is my u. My u is x squared, so u prime is 2x over, but it's negative, over 1 plus u squared. So I'd have x squared squared. So I'm going to finish this as a y prime over negative 2x divided by 1 plus x to the 4th. I don't think you'll have any problem doing inverse trig derivatives. Last little thing, it says a particle moves along the x-axis so that its position at any time where t is greater than or equal to 0 is given by the function arctan of t. A, prove that the particle is always moving to the right. Well, I'm trying to decide where I want to write. To prove that it's always moving to the right, I look at velocity. Velocity is a vector quantity. It has direction as well as a magnitude, how fast it's moving. So I need my velocity to be greater than 0, means it moves to the right. Means particle moves to the right. We learned that concept in AB. So now what I want to do is get to velocity. I have the original function. I had x equals tan inverse of t. So let's find x prime. X prime of t. This is my u, right? So the derivative of t is 1 over 1 plus t squared. No matter what value I place into t, it's going to get squared. So if t were negative, which t isn't negative anyway, is it? Because we're always, if we're talking about time, we add it to a positive one, we divide a positive by a positive. This is guaranteed to always be greater than 0. And therefore, our particle is always moving right. Part B, prove the particle is decelerating. So to prove it's decelerating, let's get to acceleration. And I do that by taking another derivative. And that looks like it will be I'm trying to think. Oh, quotient rule. There we go. Double prime. So derivative of the top is 0. Don't really need to write the bottom. Minus derivative of the bottom is a 2t times the top over bottom squared. 1 plus t squared quantity squared gives me a negative 2t over 1 plus t squared squared. What can be said about this? Well, I noticed that the top is always negative and the bottom is always positive, yielding us a negative result. So, combining, I have velocity that's greater than 0, and I have acceleration, which is less than 0. So our particle can be shown or proven to show that it is slowing down. It's decelerating. See, what's the limiting position of the particle as t approaches infinity? So part C, I want to head to infinity. I'm going to use a limit because that's probably my easiest mathematical notation to say that it's approaching infinity. And the position function was arc tan, I like to write tan inverse of t. And we're letting t go to infinity. Okay, so remember when we started this? We talked about domain and ranges, and it kind of comes back to that. The domain and range. So the domain was all reals, and the highest value I can attain in tangent is pi over 2. That's its limiting position. I wanted to take this and turn this, turn it this way though. That's not quite giving me. Anyhow, you can see how it's going to be pi over 2, but I want this, maybe I have to rotate and flip, because this should look like that as it's, because it's a reflection over the axis or the line y equals x. So my tan function becomes this. So as I head to infinity, it approaches pi over 2. Hopefully that made sense. Whoops, too far. So this is pi over 2. All right, that covers this section. Great to be with you.